Okay, let's get started. Welcome back. This is the 7th lecture of the condensed matter course. In the last lecture, we introduced a rather important simple model of vibrations in one dimension, the monatomic harmonic chain, chain of masses and springs. Every spring is the same, every mass is the same. Extremely simple model, but it introduced a lot of very important concepts to us. We solved for all of the normal modes of the chain. When we quantized the system, we discovered the meaning of phonons, what the quantization of the normal modes were. We introduced the concept of crystal momentum, the idea that if you shift a wave vector by 2 pi over a, you get back the same exact physical wave that you started with. We introduced the concept of the Brillouin zone, a range in k-space, usually taken from minus pi over a to pi over a, where all of the wave vectors are physically different waves, and if you go outside the Brillouin zone, you just start repeating the waves that you've already described. And we also managed to calculate the heat capacity of this chain exactly. And we compared it to the Debye theory and the Einstein theory that we had looked at previously. Now, one of the simplifying assumptions we used going into this model was that every single mass and every single spring in this chain were the same. And in real materials, you typically have different types of atoms. For example, in sodium chloride, you'll have a sodium atom and a chlorine atom, and these will be different. So maybe a better model of a typical material would look something like this. You'd have a light-colored atom and a dark-colored atom. I'm drawing everything in one dimension again, and then a light-colored atom and a dark-colored atom, and a light-colored atom and a dark-colored atom, and so forth. Now let me introduce some nomenclature that's going to be useful. The idea of a unit cell is the repeated motif. So for example, we can take our unit cell to be this box, and if you repeat this box over and over and you stack the boxes together with no space in between, you will reconstruct the entire chain. Another important word that we introduced last time is lattice constant, which we defined as, well, we usually call it A, and we defined it as the distance between equivalent atoms. So, for example, lattice constant would be like this. We'll call it A, from this light-colored atom to this light-colored atom. You may also notice that that lattice constant also happens to be the size of the unit cell. Draw it like this. This distance here is also A. Or if I drew it properly, it was. Now, one side comment is that the unit cell is actually not unique. Let me draw another picture of this chain. I could have drawn the unit cell equally well like this. So that's something I should probably even write down because it's important. Unit cell, not unique. And if I had chosen this as a unit cell, I could stack duplications of that together and build up the entire chain just as well. Now, what we're going to do today in a real calculation is we're going to try to calculate the normal modes of a chain that looks like this. And the reason we're doing this is not just to add complexity to a problem we already solved last time. In fact, by having different types of atoms in our chain, we're going to see that some fundamentally new and different things occur. So that's why we're doing it. So let me draw the chain. This is known as the alternating chain, or frequently known as the alternating chain, sometimes known as the diatomic chain. And it looks kind of like this. There's a dark atom, then a light atom, then a dark atom, and a light atom, and a dark atom, and a light atom, and they're connected together with springs. And so forth. And we have a lattice constant A, which is the distance between identical. Can you see the difference between the light and the dark? Have I made it clear enough? You can see that? OK. So A is the distance between equivalent atoms, so between light atom and light atom. And now we have a choice as to what model we want to write down. And there's two common choices that people make in solving. I mean, there's two separate problems, but they're similar. One choice that's frequently made is to make the mass of the light atom and the mass of the dark atom different. We're not going to solve that. You're going to actually solve that for homework. That one's a typical choice. What we're going to solve instead is we're going to make the two different springs, this spring, kappa 1, and this spring, kappa 2, different. And we're going to let them alternate back and forth. Kappa 1, kappa 2, kappa 1, kappa 2, and so forth. And hence the name alternating chain, because the springs alternate between kappa 1 and kappa 2. The physics of these two chains, whether we're letting the masses alternate or the springs alternate, is extremely, extremely similar. The reason we're doing this one is because it's algebraically just slightly easier to keep track of than the one you're going to do for homework, which is slightly algebraically more complicated. So let's write down some coordinates. So for example, let's let the light-colored atoms have positions xn, and the dark-colored atoms have position yn. So for example, let's let this one be x1, this one will be y1, this one will be x2, this one will be y2, and so forth. And now, the way we solve problems like this, these mass and spring problems, is you start by writing down Newton's equations of motion. So, well, okay, one more definition is that delta x and delta y are the deviations from equilibrium. Deviations from equilibrium position, from equilibrium. Okay. And we're going to write down Newton's equations in terms of these delta x and delta y. So maybe I'll put it on another board. Maybe I'll put it over here. So mass delta x double dot, mass times acceleration equals, we have to be a little bit careful here. On x atom, a light atom, on the right it has a kappa 2, and then on the right of an x atom is a y atom with the same number, so delta y n minus delta x n. And then on its left is a kappa 1 plus kappa 1. And on its left is a delta y atom with the index 1 lower, minus delta xn. Does everyone agree with that? That on the left of x2 is y1, so the kappa 1 spring has the lower index. Yes? Good? Happy? All right. Good. And then m delta yn double dot. OK, so on the right of a y is an x with the index 1 higher, and that's a kappa 1 spring. So delta x n plus 1 minus delta yn. And on the left is kappa 2. On the left of y1 is x1, so it's an x with the same index, delta xn minus delta yn. So I think I got that right. OK, so those are our equations of motion. And the way we're going to solve this is the same way we did last time. We will write down a wave ansatz. Wave ansatz. So there's some disagreement on what the word ansatz actually meant in German. And so someone stopped me after lecture, a German speaker, said, no, you were right about what ansatz means. And then someone else said, no, you're wrong. And then I asked a couple German speakers, and they all disagreed. And then actually someone pointed out that ansatz is actually an English word. It's in the OED. You can look it up. It means mathematical guess. So it's in there. It really is. OK. So anyway, we're going to write down our wave ansatz. So delta xn is some an e to the I omega t minus I k n a. And delta yn is, let's call it ax rather. And ay e to the I omega t minus I k n a. And what we really mean, as last time, is we mean to actually take the real part of this whole expression. And because of that, we're allowed to choose omega greater than or equal to 0. But k can be either sign, to represent either left-going or right-going waves. Now, as with last time, we realized that if you take k and you shift it to k plus 2 pi over a, you get back exactly the same wave. And the reason for that is because if you look at the exponential factor, e to the minus I k plus 2 pi over a times n is times a times n is equal to exactly the same thing as e to the I k n a. I'll make this n a so it matches. That those two are exactly the same. So if you shift k by the 2 pi over a, you get back exactly the same waveform. Rather important fact we found out last time. Just a couple other things. We're going to use periodic boundary conditions, periodic boundaries, BCs. We'll use a system of length L equals n times a. So this means we have n unit cells. And if we have a system of size L, that means the k's must be, on a periodic boundary condition, must be 2 pi over L times p, where p is an integer. So the spacing between different possible values of k are 2 pi over L. So now if we want to count the number of different k's, we did exactly the same calculation last time, different k's. That equals the range of possible k's, that's 2 pi over a, before we start repeating, since you can shift by 2 pi over a and get the same wave back. And the spacing between k's is 2 pi over L. That gives us L over a, or n. So the number of different k's is equal to the number of unit cells in the system, a rather general rule that we will use many times. OK, so given our wave ansatz up there, we can solve this set of Newton's equations just by plugging in and doing a little bit of algebra. And then I concede that the algebra I'm about to do is a little bit messy, but bear with me. So here goes. First, we'll plug in for delta xn. So two derivatives gives me minus omega squared m. Then the wave is ax e to the I omega t minus I k n a. And that equals, it equals kappa 2 times delta y n, which is ay e to the I omega t minus I k n a. And then let's do the other term over here, the other y term. So that's plus kappa 1 e to the I omega t minus I k, and then it's n minus 1 a, because of the index n minus 1. And then let's do the two x terms. So we have minus kappa 1 plus kappa 2, ax, oops, I missed an ay here, didn't I? Ay. Ax e to the I omega t minus I k and a. Is everyone happy with that? Did I do that correctly? No one objects. Seems to work. OK. And then the other equation is minus omega squared m ay e to the I omega t minus I k and a equals. And let's do the two x terms first. So we have kappa 1 ax e to the I omega t minus I k, and then the coefficient in the second equation of the index of dx with kappa 1 is n plus 1, so it's n plus 1a here. And then we have plus kappa 2 ax e to the I omega t minus I k n a, and then the two y terms minus kappa 1 plus kappa 2 ay e to the I omega t minus I k n a. A notable thing about this equation is it's the longest equation I'm going to write on the chalkboard all year long. And now it's done, so we never have to do that again. But it's not actually as complicated as it might look, because there's a bunch of exponential factors which drop out. They cancel on both sides. So we have two equations, and we can simplify it into one matrix equation. I'll write it this way. Minus m omega squared times the vector ax ay equals some big matrix times the vector ax ay. And the big matrix is, what is it? It's minus kappa 1 plus kappa 2, and then minus kappa 1 plus kappa 2 on the diagonal, kappa 1 plus kappa 2. And then the off diagonal has kappa 2 plus kappa 1 e to the I k a. That part of the exponential didn't cancel. It comes from the plus 1. And then the kappa 2 plus kappa 1 e to the minus I k a. Coming from the minus 1 in the exponential. Is everyone good with that? Agree? OK. All right. So what is this? This is an eigenvalue equation. The eigenvalue is this guy over here, minus m omega squared. And the way you solve an eigenvalue equation is by moving the m omega squared to the diagonals over on this side. Then you set the determinant equal to 0. You get the characteristic determinant or characteristic equation, or sometimes called the secular equation. If we do that, one step, m omega squared minus kappa 1 plus kappa 2 all squared minus kappa 2 plus kappa 1 e to the I k a, absolute value squared equals 0. And we can solve that rather rapidly. M omega squared equals kappa 1 plus kappa 2 plus or minus absolute value kappa 2 plus kappa 1 e to the I k a. And that's our solution. Now, one thing you may notice is that for each k, there are two possible solutions of omega, the plus solution and the minus solution, right? So what does that mean? We'll write it down over here. Each k has two normal modes. We can call them omega plus and minus. Okay? And how many k's do we have? The number of k's are equal to the number of unit cells, and each k has 2 times 2 normal modes. So number of normal modes equals 2 times number of unit cells equals the number of masses. And this we should have expected, because we had that number of masses is the number of degrees of freedom we have. So when we solve this problem, we should have exactly that many normal modes, and indeed we do. So that's good. Good? Everyone happy with that? All right. Good. Now, so it's useful to actually plot this thing, and I'm going to sketch it out first, and then we'll sort of justify why it looks the way it does. So here I'm going to plot. Here's k. Here's omega. Okay. Pi over a. Here's minus pi over a. Minus pi over a. So that's the Brillouin zone. Outside of the Brillouin zone, everything just repeats. So we should have a mode that looks like this. And then a higher frequency mode maybe looks like this. Okay? And then you could actually reproduce this periodically outside. I mean, you can make it go onwards as you like, because as you shift everything by 2 pi over a, you just get back the same wave. But we're going to really focus on the Brillouin zone, because within the Brillouin zone here, every wave you find is different from every other wave. Now, it's useful here to probably look a little bit more carefully at this plot and see why it looks the way I've drawn it. So let's look at some convenient points, maybe at k equals 0. That's a good point to look at. Well, what happens with k equals 0? So over here, we have this absolute k2 plus k1 e to the I k a. That goes to just k2 plus k1. So m omega squared is either 2 times k1 plus k2, or it's 0. And so I've drawn that here. Here's 0 at k equals 0. And here is the higher energy one. Maybe let's draw the higher energy one also. So omega plus at k equals 0 is square root of 2 kappa 1 plus kappa 2 over m. Did I get that right? I think so. So that point here, we'll give it square root of 2 kappa 1 plus kappa 2 over m. And so we have the low energy mode and we have the high energy mode. Now, the low energy mode, we'll come back to the high energy mode in a moment, but the low energy or low frequency mode is one that we should expect should have been there. because we should expect that there should be sound waves somewhere in this system. And when there are sound waves, we know the sound waves should have a spectrum which has frequency linear in wave vector and comes down to 0 at 0 wave vector. Now, to convince ourselves that that's what's going on with this equation, we have to actually do a little bit of more math and expand the dispersion curve near k equals 0. So let's see how we do that. So let's take k2 plus k1 e to the I ka. That quantity there is, well, yeah, that thing there can be written as square root of kappa 2 squared plus kappa 1 squared plus 2 kappa 1 kappa 2 cosine of ka. Just by multiplying that out. And if k is small, we're going to replace this cosine by 1 minus ka squared over 2. So then what we have is, I guess we can write it like this, square root of this whole thing of kappa 2 plus kappa 1 squared. That takes care of the 1 term. When I put together this, this, and this, I get kappa 1 plus kappa 2 squared. And then what's left over is, oops, 2's cancel, kappa 1, kappa 2, ka squared. I get that? Everyone agree with that? Yeah? OK. Then this conveniently factors out to give a kappa 2 plus kappa 1 times the square root of 1 plus kappa 1, kappa 2, ka squared over kappa 1 plus kappa 2 squared. And if you remember, square root of 1 plus x, oops, did I get a sign wrong? I got a sign wrong. That's minus. That's minus. No one gets chocolate for that. Is 1 minus x over 2. So then we can rewrite this as kappa 2 plus kappa 1 minus kappa 1, kappa 2, ka squared over 2, kappa 1 plus kappa 2. Does that look right? Did I miss anything? Yeah, kappa 1 plus kappa 2, thank you. Kappa 1 plus kappa 2, yeah. Yeah, good, thank you. Whoever said that, I owe them a chocolate. So, yeah, okay, okay, good. So I don't have one today. I was going to bring one, but I ate it. So, all right, so if I plug that into here, we see that the kappa 1 plus kappa 2 with the minus solution cancels this kappa 1 plus kappa 2 also will cancel this, and we'll end up just getting m omega squared. M omega squared equals kappa 1 kappa 2 ka squared over 2 kappa 1 plus kappa 2, or equivalently, omega is square root kappa 1 kappa 2 a squared over 2 kappa 1 plus kappa 2. I guess there's an m down there, and then absolute k. Whew. All right, and I realize that's a lot of math. We're not going to do too much math that heavy this year, but I have to do it once in a while. OK, so this we recognize as the sound velocity. So we just derived the sound velocity of this wave. The sound velocity is the slope of this curve here. Now, usually, actually, I should use the proper nomenclature. Usually, people refer to this as the acoustic mode. And they tend to call it the acoustic mode even all the way out to the zone boundary out here at very high k, even though it's really only sound when it's long wavelength or small k. They call the whole branch here the acoustic mode. Now, you remember last time when we derived the sound velocity, we also were able to derive the same sound velocity by using a hydrodynamic argument. So let's see if we can do that again this time. Remember, from hydrodynamics, we have that the v sound should equal square root of 1 over the mass density times the compressibility. The mass density is, well, there are two masses per lattice constant A. And the compressibility, well, we derived last time, the compressibility should be 1 over the spring constant times A. And the spring constant, well, here, the unit cell has 2 springs in it. And the spring constant for 2 springs in series is kappa 1, kappa 2 over kappa 1 plus kappa 2. Does that sound familiar? Remember that from first year? OK. So if we plug this and this and this into here, in fact, we get exactly the same result. V sound equals square root kappa 1, kappa 2, A squared over 2m kappa 1 plus kappa 2. So the hydrodynamic calculation gives you exactly the same result as we got by actually solving the system completely. Now let's talk about this mode up here. This mode is known, in comparison to the acoustic mode, this mode is known as the optical mode. Optical mode. High frequency mode at k equals 0. And we should probably, I should probably tell you why the name optical mode. So the word optical mode comes from experiments on real materials when you shine light on the material and you induce vibrations by shining light on it. Now, if you think for a second, what's the property of light that we know, similar to sound? Light has frequency which is proportional to its wave vector. The only big difference is that c is huge compared to sound velocity. So if I drew the light dispersion curve on the same plot, it would be an extremely steep sloped line like this. Probably so steep I couldn't even draw it. Now, if you imagine shining light on a material and creating vibrations, in quantum mechanics we should think about absorbing a photon and creating a phonon. So imagine a process where you absorb a photon and create a phonon. In order for that to happen, you have to conserve both energy and momentum. So you have to match up both the frequency and the wave vector of the light with the frequency and the wave vector of a phonon. The only place that can happen is right here. And the reason you're never going to match the acoustic mode because the velocity mismatches so badly. But with the optical mode, since the optical mode has finite frequency even at k equals 0, there is a point where the optical mode frequency matches the light frequency and the optical mode momentum matches the light momentum, or even crystal momentum in this case. Now, so that's the nomenclature of why people call this the optical mode. Whenever you have interactions with light and vibrations, it's inevitably the optical mode. But I should be a little bit honest that that process I described to you, by which you absorb a photon and you emit a phonon, actually does not occur. And the reason it doesn't occur is because there's a conserved quantum number, the spin of the photon, which, photons have spin, phonons do not. So if that process were to occur, you would violate angular momentum conservation. So that's, definitely bad. You don't want to violate angular momentum conservation. So in fact, no such process exists by which a single photon is absorbed and a single phonon is created. However, there are more complicated processes that can occur involving photons and phonons. For example, absorb 2 photons and emit some phonons. That's OK because the angular momentum of the 2 photons can cancel, and you can still have conservation. And it's still the same principle that it's very hard to conserve both energy and momentum in any sort of interaction between phonons and photons unless you're getting optical modes into the game, because you need to get high frequencies into the game somehow with phonons. And the only way to get high frequencies with small wave vectors in phonons is to use the optical mode. OK? So that's where the name comes from. Actually, more generally, let me give more general nomenclature here. Acoustic mode, generally, acoustic mode is any mode where omega is proportional to k at small k. And optical mode is any mode where omega goes to a constant not equal to 0 at small k. OK, so let's think about this small k regime a little bit more seriously. So we found the eigenvalues, the frequencies, but let's look at the eigenvectors. So the matrix we're actually diagonalizing is that big matrix there, and let's look at it at k equals 0. So at k equals 0, the matrix we're interested in is of the form, I guess it's minus kappa 1 plus kappa 2 times, what is it, 1 minus 1 minus 1, 1, something like that. Or did I get the minuses in the wrong place? No, I think it's right. OK. So it looks something like this. Because when the wave vector goes to 0, the exponentials, e to the ika, both go to 1. And so you have a matrix of the form 1, 1 minus 1 minus 1, 1. If I pull out minus kappa 1 plus kappa 2. So the eigenvectors, we have two possible eigenvectors. One is for the omega equals 0 solution. We have an eigenvector ax, ay equals 1, 1. Whereas for the optical mode solution, the other eigenvector, the high energy, high frequency eigenvector, we have ax, ay equals 1 minus 1. So what is this telling us? What this is telling us is that for the acoustic mode near k equals 0, the atoms are actually moving with their neighbors, that both of the atoms in the unit cell are moving in the same direction at the same time. They're moving in concert. Whereas for the optical mode, the higher frequency mode, the two atoms in the unit cell are moving opposite each other. And it's actually quite natural to explain then why it is that the optical mode is so much higher in frequency, because in the optical mode you're compressing the springs maximally, whereas in the acoustic mode you're hardly compressing the springs at all because everyone is moving in the same direction. Now these sort of trends occur more generally. So general, if there are m atoms in the unit cell, we would have m modes at each k. One is acoustic. That's the mode where everyone moves in the same direction at k equals 0. And then the remaining m minus 1 of them are optical, meaning they don't all move in the same direction at k equals 0. In d dimensions, there are d times m modes at each k. D are acoustic, and the remaining d times m minus 1 are optical. OK, why is this? Well, the total count of the modes is the total count of the number of degrees of freedom. If there are m, there's always the same number of k's as the number of unit cells in the system. Each unit cell has m masses in it, and they can move in d dimensions. So there's a total of dm degrees of freedom per unit cell. So we expect dm modes for each k. Now, of them, there can be d of them that are acoustic, and that corresponds to all of the masses moving in any of the three possible directions. So we know what these things are. We've discussed them before. One of them is longitudinal, and two of them are transverse. So for each k, one of them is moving in the direction of k, and then two of them are moving perpendicular to k in 3 dimensions. OK, there's one more point on this picture that we should probably look at more carefully, which is these interesting points here, which are at the so-called Brillouin zone boundary, pi over a. Let me put it over here. So consider BZ boundary, k equals pi over a. So what do we have then? Well, then this factor kappa 2 plus e to the I ka kappa 1 is actually absolute k2 minus k1. And so the frequencies, omega squared is 1 over m, k1 plus kappa 1 plus kappa 2, plus or minus absolute kappa 1 minus kappa 2, or kappa 2 minus kappa 1, doesn't matter. It's absolute value. And that means that we have two possible solutions. Omega equals either square root of 2 kappa 1 over m or square root of 2 kappa 2 over m. So we'll mark them here. So this one we'll call square root of 2 kappa 1 over m, and this one we'll call square root of 2 kappa 2 over m. And here I've assumed that kappa 1 is greater than kappa 2. Otherwise, it would be the other way around. The higher energy one is always on top. And these modes actually never cross each other. You can convince yourself by looking at the form of the frequency. These two modes can never actually cross. So what's going on at this Brillouin zone boundary? At the Brillouin zone boundary, the waveform delta x delta y equals ax ay e to the I omega t e to the minus I k n a. This e to the minus I k n a becomes minus 1 to the n. And that tells us that what's going on is that alternate unit cells are moving out of phase with each other. They're moving in the opposite direction as each other. So now let's see if we can get this to work. Uh-oh. No, stop. Stop. No. Oh dear. Does this happen only on Mondays? Here we go, screen up. Okay. But that's on. Oh wow, amazing. Okay, so we can still do this while it's going on. Okay, so this program is the thing written by Mike Glazer. And you can click alternating chain and longitudinal. Longitudinal means that everything oscillates in the single line. You can change the k here by changing this slider. And you can see that the dispersion is plotted down here. It's plotted from 0 to 2 pi instead of minus pi over 0 to 2 pi over a instead of minus pi over a to pi over a like I've drawn here. But it's the same picture. So first let's start by taking k very, very small. Oh, and also you have these little clickers up here which will change the masses on the springs. Let's make the masses the same. And C1 and C2 are what we call kappa 1 and kappa 2, the two spring constants. So we have two different spring constants, kappa 1 and kappa 2. And here's the dispersion, the acoustic mode down here, the optical mode up here. Here we've clicked acoustic, so we're seeing actually the acoustic mode here. And you see that the acoustic mode is very low frequency. And basically all of the, let's move this up a little bit so it happens a little faster. You can see that basically all of the masses are moving in concert with each other, sort of slow sloshing back and forth, hydrodynamic oscillations. So you can sort of viewed as one big fluid, everything sort of moves together. Now if we go to k equals 0, it becomes 0 frequency, but we can click on optic here and we'll get the optical mode. You see the optical mode is each mass moving opposite the other mass in the unit cell. And you can see that this is something that should be high frequency because it's compressing the springs maximally. Now if we then change the k vector to the Brillouin zone boundary, what we have here is as predicted, that the alternate unit cells are moving opposite each other. So this unit cell, these two masses, are moving opposite of these two masses. And you can see actually why it is that only one of the two spring constants enters in the frequency, because the spring between these two masses actually isn't getting compressed at all. It's only the spring between the unit cells that are getting compressed, and not the spring within the unit cell that's getting compressed. Now, if you switch then from looking at the optical mode at the zone boundary to the acoustic mode at the zone boundary, it looks extremely similar, but it's lower frequency here. But you'll notice it's the other spring that's now getting compressed. It's still, you have one unit cell moving in one direction, another unit cell moving in the opposite direction, but now it's the opposite spring, the K2 spring, which is being compressed rather than the kappa 1 spring being compressed. Okay? So I highly recommend that people download this program and mess around with it. It's got a lot of other fun features. This is what we can do on a boring Saturday night or something. Okay, so let me redraw this picture here. Maybe stop this for a second. Okay, redraw this picture here. All right, I don't know why it's still doing that, but okay. All right, good. Let me redraw this picture, except I'm going to draw it slightly differently. Here's K again. here's omega. And I'm going to put pi over a here, and minus pi over a here, and then 2 pi over a here, and then minus 2 pi over a here. I'm going to draw the acoustic mode just like I had it before. And then the optical mode, what we had before was something that looked like this. But I'm perfectly allowed to take this piece here and shift it by 2 pi over a and plot it instead here. Okay? So all I did was I took this piece and I shifted it by 2 pi over a to move it over here. And then I can take this piece here and shift it 2 pi over a this way and put it here. Okay? So now I'm going to erase. I know people hate when you do eraser transforms. I'm going to erase the piece in the middle, and I'm going to leave these pieces here. So I have this piece, and I have this piece. Okay? So just took this piece and moved it by 2 pi over a this way, and this piece moved it by 2 pi over a that way, and I got this picture here. Now, this way of drawing things is known as the extended zone scheme. Extended zone scheme. And it has a nice advantage that there is only one k, there's only one mode at each frequency, at each wave vector k. So whereas over here, we have 2 modes at each wave vector k. Here we only have 1, but we've used twice as much range of k, and that's sometimes convenient to do. Just some nomenclature, which is useful. This range here is known as the first Brillouin zone. Brillouin zone. And this region here is known as the second Brillouin zone, along with this region here. Second Brillouin zone. So we took the optical mode and we moved it out of the first Brillouin zone and put it into the second Brillouin zone for the extended zone scheme. This way of drawing things over here, in comparison to the extended zone scheme, is known as the reduced zone scheme, because everything has been reduced into a single Brillouin zone. Now, why is it that it's so convenient to spread everything out so that there's only one mode at each wave vector? Well, a case where this becomes extremely useful to do is the following case. Suppose, consider kappa 1 very close to kappa 2. So in that case, what's going to happen is that this little gap here is going to get extremely small. So let's see what that looks like. So here's k. Here's pi over a. Here's 2 pi over a. Here's minus pi over a. And here's minus 2 pi over a. So what it's going to look like is kind of this, that, like this, like that. So a very small gap at the Brillouin zone boundary here, because kappa 1 and kappa 2 are very close to each other. Now, what happens when kappa 1 actually equals kappa 2? Well, then what we have is the gap closes. It becomes a single connected line. But more importantly, we recover the monatomic chain. Right? If kappa 1 equals kappa 2, then every mass and every spring is the same as every other spring. Every mass is the same as every other spring. So we get back the monatomic chain. But the lattice constant has changed. The new lattice constant is only half as big as the old lattice constant, because the white and black masses now actually are the same. They're the same object now, so we don't have to make a unit cell with 2 things. We now make a unit cell with only 1 thing in it, right? So the Brillouin zone, the BZ, now ranges from k, goes from minus pi over a prime to pi over a prime. Okay? And that is the same as 2 pi over a, minus 2 pi over a to 2 pi over a. Okay? So this entire range here, if the 2 masses become the same, this entire range here becomes the first Brillouin zone, first BZ of monatomic chain. Monatomic chain. And then if you make kappa 1 and kappa 2 slightly unequal, you open a small gap at the new Brillouin zone boundaries at pi over a. Okay? But really, what's underlying is a single mode for the monatomic chain from here to here and here to here, just a single connected mode. And you open up, when you make kappa 1 and kappa 2 slightly different, you open up a small gap at the Brillouin zone boundary with the new smaller Brillouin zone associated with the new larger unit cell. Okay? Happy? Okay. In the last few minutes, I want to discuss a completely different topic, something we didn't get to last time, which was, or the time before, which is van der Waals bonding. Van der Waals, you may remember this guy from the van der Waals equation of state that you probably studied in Stat Mech. Van der Waals bonds, also known as molecular bonds, molecular or fluctuating dipole bonds. And these are, van der Waals bonds are actually quite different from either ionic or covalent or hydrogen or metallic bonds in the sense that these bonds occur for inactive chemical species. And what I mean by inactive species is that no electron is transferred between atoms, no electron is shared between atoms. Things like noble gases are classic cases of van der Waals bonding. The noble gas has a filled shell. It doesn't share its electrons. It doesn't donate its electrons. It doesn't covalently bond. It doesn't ionically bond. But it can still van der Waals bond. Now, another example of an inactive species are molecules such as nitrogen 2. Nitrogen by itself as an atom is very active. But when you put two nitrogen atoms together, they form a nitrogen molecule, which is extremely inactive. You can think of it as being filled molecular shell, and it also does not share. Once you have the molecule is very stable. It doesn't share its electrons with anything else, and it doesn't donate its electrons to anything else. So, nonetheless, even though you're not donating electrons or moving electrons around, you can still, running out of space, you can still form a bond. The way the bond occurs is as follows. Imagine that you have, say, a nice noble gas atom over here, and maybe another nice noble gas atom over here. And suppose at some moment this atom has some dipole vector P1, a polarization. Now, if you remember from your E&M, a distance r away, there will be an electric field due to that dipole moment, in this case pointing in that direction. And E will be equal to minus P1 over 4 pi epsilon naught r cubed. And if I had drawn the angles differently, I conveniently chose r to be perpendicular to the moment there. But if I didn't make them perpendicular, there would be some cosines and sines and stuff like that, which I'm leaving out. Now, when this atom experiences this electric field, it develops a polarization. It gets an induced polarization, P2, which is chi, some constant, times E. And this constant here is known as the polarizability, or electric susceptibility, and you can calculate this, for simple atoms like hydrogen, you can calculate the susceptibility, in perturbation theory. And maybe you've even done that as an exercise. There's an exercise in the book that asks you to do that using quantum mechanics. Anyway, now what we have is we have two dipole moments. And you'll remember that the energy of two dipole moments is minus P1, P2 over 4 pi epsilon naught r cubed. So the total energy is then, just plugging these things all together, we get minus P1 squared chi over 4 pi epsilon naught r cubed, all squared. And in particular, this is negative and goes as r to the 6th. So the force goes as 1 over r to the 7th. Now, that's more or less how the calculation goes, that you have a polarization in one atom, it induces a polarization in the other atom, and the polarizations attract. But you might say, well, wait a second. This whole argument was predicated on the statement that the polarization is not equal to 0 to begin with. But in a spherically symmetric atom like helium, the expectation of the polarization is 0. Why is that? Well, you remember that the polarization of an atom, here's the nucleus, here's the electron. The electron's running around the atom in some sort of spherical orbit. So the position, r, of the electron is related to the polarization just by minus e times r or something like that. So it's really, we're just saying that the average position of the electron is actually at 0. But you'll notice that what actually comes into this equation is not the polarization or the dipole moment p, but it's p squared. So p squared is not equal to 0. So that you can get a non-zero dipolar attractive force, even though the average dipole moment is 0. If you like to think about fluctuations in quantum mechanics as being some sort of dynamical fluctuation or fluctuation in time, what we really mean is that it's a sort of a coarse picture or a crude picture of what quantum mechanics is, but you can sort of think of it as at some moment in time the electron is on one side of the nucleus, so there's a dipole moment. The other atom responds to that and orients its dipole moment in the opposite direction, and they attract. And then at some later time, there's a question? Yeah, if there's an angle between P, you're saying that if there's an angle between P1 and P2, there would be cosine thetas and so forth, and things like that. Yeah, but the force will still be attractive. You can, and actually, there's an exercise in the book that works you through it, and you can get all the angles right, and it will always come out attractive. Good question, but not worth a chocolate bar. So, but it's still a good question. Thank you. Anyway, so it's basically you get a little bit of a fluctuation on one atom. It causes a fluctuation in the other atom, and they attract. And no matter which direction the fluctuation is, the responding fluctuation is in the opposite direction, and they always attract. So you can still get a non-zero van der Waals force. Now, the van der Waals force is much weaker than covalent, ionic, or hydrogen bond, but it's still strong enough to cause important effects, such as it holds together things like argon at low temperature when argon becomes a solid. A more interesting case of where van der Waals forces show up is with this guy. If you've ever been to tropical climate, this is a gecko, a little lizard. They sell car insurance in the United States. I don't know why, but it's true. This is the mascot of the Geico Gecko company. Anyway, geckos are amazing little creatures because they can crawl up almost completely flat glass walls with no trouble at all. And the thing that actually sticks them to the wall turns out to be van der Waals forces. They have very flat foot, and they stick their foot onto the glass, and there's enough van der Waals force between their foot and the glass, and they're fairly light little creatures, that they can actually walk up the wall because of that. All right, I apologize I went over it. I will see you on Wednesday.